Thank you very much. It's my pleasure to introduce Professor Davidson from Curtin University, Western Australia. David has a long career in the area of computational electromagnetics and its application, particularly to in radio astronomy. He started his career at the University of Stellenbosch. He holds degrees of PhD and Doctor of Engineering from that institution, and he spent many years there until 2017, I think, as a leading researcher in electromagnetics with focus on the development of the SKA in the South African part. In 2018, he moved to Curtin University, where he became to be involved in the same activities, but in the Australian part, the SKA that is being developed in Western Australia. He has been a lead development person in the development of the International Centre for Radio Astronomy Research. He has been, as I say, strongly developing that. He's been particularly involved in the development of the SKA low, which is in the part of Western Australia, about 600 or 700 kilometres north of Perth. He's going to talk to us today about the impact of computational electromagnetics in the development of radio telescopes such as SKA low and others. David.
Paul, thank you very much for the introduction, and thank you very much for the kind invitation to give this talk. So the title of the talk is The Impact of Computational Electromagnetics, which I had to shorten up because the slide didn't have enough space, on the new generation of radio telescopes. And you may notice that I've dual badged myself. I'm employed by Curtin University, but I also have an appointment at Stellenbosch University, where, as was quite rightly said, I was a professor for 30 years. So I'm Professor Emeritus there and also an extraordinary professor. I would like to acknowledge up front some very specific contributions from my colleagues, specifically at Curtin, or formerly at Curtin. That includes Maria Kovaleva, Martin Sokolovsky, Adrian Satinjo, Daniel Ung, and Randall Waith. A significant number of them are in the audience here. I also have colleagues overseas, such as Pietro Bolli and his colleagues at INAF, that's the Italian National Astrophysics Foundation. I'd also like to acknowledge a couple of people I've not put on the list there, Stefan Weinholz at Astron, we worked closely together for many years, and also Carl Warnick from BYU in the United States. So, what you're seeing in the picture over there is one of the first, actually the first SKA station, I think it's station number 8, and it shows 6 of the eventual 500 stations that will be deployed in Western Australia. And I'll talk about this in considerably more detail as the talk progresses. Sorry. Let me give you an overview of what I want to talk about. And while I was preparing the talk, I thought this talk actually very nicely splits into the two real aspects or parts of my career. For about the first 20 years, my very first job was actually at the CSIR in South Africa, which is like CSIRO in Australia. And we were working at that time on defense electronics, and particularly electronic warfare. For about the next 20 years, I worked primarily on advancing computational electromagnetics. I was closely involved with the development of the simulation package FECO, or FECO, depending on how you pronounce it. Both my students and myself contributed, both in terms of developing it, applying it, and I wrote some of the core parts of the final element part of that code. I have to say, it's got such a new interface now, I have trouble using code that I wrote many, many years back myself. The second 20 years of my career, and that started around 2005, was when South Africa became involved in the SKA. A number of other countries had been pushing the SKA, in particular the Netherlands, England, Australia. But in around the early 2000s, South Africa became interested and put in a very concerted and well-managed bid, which eventually resulted in South Africa building Meerkat and getting SKA mid. So that was the start of my interest in radio astronomy, and for the last 20 years, the main focus of my work has been more on applying existing techniques into new fields, in particular radio telescopes. I also thought, just while I was listening to some of the introductory work and that focus on the Young Scientist Program, it took me back 33 years ago in 1992. The very first URSI conference I attended was actually here in Australia. I think it was a Commission B meeting. It was where I was introduced to Professor Georgios Lengi, who's made massive contributions. He set up the IEEE in terms of wireless propagation letters. He founded the ICIA conference series, which runs now every year, and the next one is in a couple of weeks in Italy. And he also has left a great legacy in URSI. So, George, it was wonderful meeting you 33 years ago. A couple of years back, I was in Sydney with my wife and family, and I said to the guide, "Oh, yes, I've been here before, and I was at the conference in 1992. And he said, "No, you weren't. We knocked it down in about 2005 and built a completely new conference centre," which is where we are now. So, the theme of the talk is how the computational techniques, which initially were developed in the early 1960s and took many years to come to fruition in industry, how they've impacted on the new builds of radio telescopes. And I think it's fair to say that the SKA low and mid are probably the first major instruments where our ability to now simulate what I call full-wave electromagnetics, in other words, not optical, it's not just really dish optics, but really understanding what's going on right down at fundamental level, has allowed us to understand how these telescopes are going to work. I do need, because this is a general lecture, I'm going to spend a couple of minutes talking about what an interferometric or aperture synthesis radio telescope is. Many of us have, when we talk about a radio telescope, we think of the Parkes dish, or we think about the big dishes in Socorro in New Mexico as part of the Very Large Array. But most modern radio telescopes are a little bit different to that, and I'll talk about why that's the case. I'm going to briefly also talk about computational electromagnetics and relevant CEM methods. This is not a lecture where I'm going to dive deep into it. Obviously, I've done that at many times during my career. But I'm again conscious this is all the URSI commissions. Paul and I were talking very briefly now, and we realized that something like about half the URSI commissions were involved in SKA. But this talk is really going to focus primarily on the Commission B and Commission J work, which is EM theory and obviously radio astronomy. I'm going to go into SKA low in some detail. I am also conscious that SKA-O is now an intergovernment organization, an observatory, and they're the people who are constructing telescopes. And shortly after tea, just after this talk and after tea, Lewis Ball, the Director of Operations, will be giving you an update about the project. So I'm a little conscious of not stealing his thunder, so once or twice there's a video that I was going to show, then I realized Lewis is talking, so I'll defer that to Lewis to show you. I'm also going to talk a little bit about dishes, such as Meerkat, and another type of array, focal plane arrays, which we have one in Australia, ASCAP, which CSIRO drove, and I'll just talk about how computational methods has impacted on those. I've already acknowledged a number of specific individuals, but generally there's been a large number of engineers working on this. I think at some of the last SK engineering meetings, there were several hundred engineers attending and scientists, so it's a big community that does this sort of project. Picking up again on some earlier themes of collaboration, this is way too big a project to do yourself. Just quickly about the SK Observatory. The SK Observatory is the successor organization to the SK organization. The SK organization was a somewhat looser affiliation of member countries, although it was constituted in the UK as a company. The SK Observatory is an intergovernment organization, so it has the same sort of status as the European Southern Observatory and CERN, and its job is to build the world's largest radio telescope. The host nations we mentioned already. Australia has the SKA Low telescope. South Africa has the Mid telescope. You might wonder what happened to the SKA High telescope, and I'll defer that question to Lewis. And also the UK hosts the headquarters. There are actually 12 members and a number of other countries which I think have observer status, and the member states as of January 2025 are listed there. On the right of the image there is the classic Lovell telescope. That's about a 250-foot, 76-meter dish. It was built in the late 1950s. It's older than I am, which is fantastic, and it's still working, which is inspirational. In front of it is the new SKA headquarters, and there's also a very nice visitor centre now, which is something new at Jodrell Bank. So let me dive now into a little bit more detail about what an interferometric telescope array is. Much of the time, radio telescopes such as the SKA are busy with essentially mapping the skies. Now, they have another operation as well. They can also operate in what antenna engineers would just call a phased array. They call it a tied beam array, and essentially all the beams just point in a particular direction, and it's typically used for pulses. But when you're making maps using interferometric imaging, you go for long baselines to get fine angular resolution, and you go for a lot of receiving systems, either antennas like dishes or antennas in the form of stations, arrays of smaller antennas. Those give you the sensitivity. And you then put it through signal processing techniques. I'm oversimplifying now. Those of you who are experts in signal processing, such as my colleagues Randall and Stefan, will appreciate this, but essentially you're doing a two-dimensional Fourier-like transform to form the image. In particular, with these wide field of view instruments, it's more complex, but for the traditional instruments, it's actually a good approximation. Here's a really simple cartoon of a 3-element interferometer. Now, again, this is way too small to do any serious science with, although 7-element interferometers were not uncommon in some of the early days, such as the Ryle system at Cambridge. There's a couple of key points over here. The first point, we have 3 dishes. I don't think there's a pointer on here, unfortunately. Oh, there is one. So there's 3 dishes. These could equally well be SKA low stations, which are aperture arrays. We have baselines. These need to be measured out very accurately using geodesic techniques, etc., after you've built the array. And there are some other techniques to do that as well. From each of the antennas, you take a cable with known properties and known length, and each of the voltages or the signals coming out of the antennas are multiplied together. These form what in engineering terms would be a cross-correlation, and in radio astronomy terms is called a visibility. So these visibilities or cross-correlations are grouped together into a 2-dimensional array. Now, with only 3 elements, you've only got 3 baselines, so that's a very, very, very sparse array altogether. In reality, you have many more baselines, and you actually have a proper 2-dimensional array. That is then Fourier transformed in 2 dimensions to give you the brightness matrix, or essentially the map of the sky. And within that, you then get the various point sources and the distributed sources on the sky, which is of interest to the astronomers. This is a really low-level, very coarse description of the process. There's a lot more detail, but I'm not going to go into that over here. There are a couple of important points. And one important point over here is that these cable lengths and the phases are known. So the whole system is phase coherent. You can track the phase through the whole part of a radio telescope. And that's fundamentally what distinguishes a radio telescope from an optical telescope. With an optical telescope, the frequency is too high, the wavelengths are too short. You can no longer make a phase coherent system, but you can do other stuff, obviously, with optical systems. So that's an important point, or one of the main differences. So here is the SKA low aperture array. Now, it was described earlier as being near Perth. Now, if you live in Australia, I guess 600 or 700 kilometers is, yeah, it's near. I mean, it's only about a day drive or something like that. It's in the Murchison Shire. Its correct name now is the Inyaramanya Ilgari Bundara, and my apologies for not pronouncing that correctly, which means sharing sky and stars in the local Aboriginal language. The Murchison Radio Astronomy Observatory, and it's normally just called the site because that's a fairly long name. It's in Western Australia, approximately 600 kilometres northeast of Perth. We like to joke that it's an area the size of the Netherlands with a population, permanent population of about 100 people. So it's a very, very low population density. I think we worked it out there, 0.002 of a person per square kilometre. And now it's significantly higher than that because we have, well, the SKA Observatory has a number of the order of several hundred construction workers on site. But when they're finished, they will leave, and we're back to a very low population of humans. There's a very high population of kangaroos, and if you drive around there, you've got to be super careful not to knock into them. This is one of the antennas, which I'll be talking about a little bit later. This was the first antenna day, which SKAO hosted last year. And there's an antenna being installed. As you can see, this is a dual polarized log periodic dipole array. It's on a wire mesh. The mesh is approximately 40 meters in diameter. You're seeing one going down there, and these are some of the SKAO technicians doing this. There's something like another 255 to go into that mesh, and then that will be replicated around 500 times across the whole site. I'm actually building one over here, and I'd just like to make an important announcement that I did remember to wash my shirt. The black dots in it are flies. So this is a tough working environment. The Murchison is normally either too hot or occasionally too cold. When it gets wet, it gets surprisingly wet. It's so flat it doesn't drain, so the water remains there for weeks on end. It can be very windy, and there are always lots of flies, so not the easiest working conditions. There was the president of the society who spoke just now mentioned briefly spiral arms and the layout of the antennas. It's worthwhile just talking a little bit more about why it's laid out as it is. So this is the central part of SKA, and here's an image of it. There's nothing there. It was cleared to deploy the core site. I think Lewis will talk about this after the tea break. But essentially, there were some delays, so it was decided to rather progress with the outlier stations rather than the core. This, in a few years, will be full of somewhere in the order of about 50 or 60,000 of those SK antennas, with around a couple of hundred stations crouched into this area. It's pretty dense. This is the east-west and north-south layout in kilometers, and approximately half of all the antennas will be in this very dense central area, and that is essentially for applications that require dense cores, close antennas, short baselines, and that stuff like pulsar imaging. There are other applications as well. Now, one of the very first questions I asked when I first saw the SK, and a question I get asked all the time, is why does the SK have spiral arms? So here are the three spiral arms, well, spiral-ish arms. This has evolved depending upon a variety of things like road layouts. Sometimes you have to avoid sites which are sensitive to the Aboriginal people, so you have some constraints sort of ground map in terms of where you can put things. But the issue fundamentally here is that's not necessarily the ideal for the astronomers. There are theoretical methods for laying out an optimal array. I think it's called a Relo triangle, and my colleague Randall built one a year or two back for educational purposes. But it's a bit difficult to configure in somewhere like SKA, or at least on the Murchison. So instead, a semi-random layout, which is what's been done in the core, is good, but you can't have a semi-random layout in an area which has got essentially no services at all. You need to get power, you need to get fiber, and you need to get roads to these sites. So the compromise was to use spiral arms that you can build roads along, where you can have the trenching done to put in the power cables and the fiber, the data communications, and that's how it's being laid out. This is on a much wider area. I think the maximum baseline is 70-something, 78 kilometers, and you'll see this runs over from -40 to +40 and -40 to +40 kilometers. The CSIRO has another program in place at the moment to look at much, much longer baselines for VLBI work, and that's another project which is on the go, but I won't talk about that because that's CSIRO's work. So that's essentially the thinking behind why SK looks like it does. Zooming down into the station, which is kind of where most of our own work has been focused, each of the station consists of it consists exactly of 256 dual polarized log periodic dipole antennas. They're mounted vertically on a wire mesh, and the ground plane is approximately 40 meters in diameter, and the maximum spacing between antennas centers is 38 meters. I'll be talking a little bit more about that in a moment. It's also interesting to note that we use RF over fiber, so right up in the top of the I'm hitting the wrong button. Right up at the top of the antenna over there, we have a low noise amplifier. We actually have two because it's dual polarized. It's not immediately obvious to look at, but this is a dual polarized system. There's an X and a Y, an east-west and north-south arm. That was in the original prototypes. They are now slightly rotated, so the east-west, north-south alignment is no longer valid, but it's a good way still to think about the stations. That system has got RF over fiber coming down over here, going across a ground mesh. And although you can't see it in these pictures, there's another one coming a little bit later where we actually have things called tile processing modules, or SK has them. And these are essentially right up front digitization stations. So within about 10 meters, with a short run of RF over fiber, the data is digitized, and the whole system is digital essentially from the front end. And that's very powerful for beamforming. And there's a few other engineering specs which are given over there. The correlation, in other words, the multiplication to form the visibilities, will now be done away from the site in Perth at the Pawsey Supercomputer Centre. Now, a good question which I alluded to earlier, when most people ask what does a radio telescope look like, what they usually say is a dish. And if you're not in the field, people usually talk about satellite dishes, which can be a bit frustrating if you're a radio astronomer. It's partly our own fault because a number of radio telescopes are actually repurposed satellite communication dishes. The South African Hartbeespoort system is an old NASA deep space tracking network dish dating back to the 1960s. And there's a big program in Africa to repurpose satellite communication dishes for radio astronomy. So it's not an unreasonable mistake for people outside our field to make. Where do these aperture arrays come from? They don't look anything like a dish. The reason is that quite a few years back, in a period called SCADS, Square Kilometre Array Design Studies, detailed engineering studies were done on how much it costs to build really big dishes. Now, somewhere like Arecibo has got a diameter of 300 meters, and the Chinese FAST, 500-meter aperture spherical telescope, as the name says, has got an aperture of 500 meters. These are very expensive to build, and the rule of thumb is that the dish cost goes up as the dish size in meters to the power 2.7. The collecting area obviously only is going up as the square of the diameter. So below a certain point, and there have been some quite vicious arguments in the community about what frequency that actually is, it's cheaper to build an aperture array than to build a dish. Generally, it's acknowledged as being somewhere around between 200 and 400 megahertz, but exactly what the frequency is depends a little bit on the economics and the cost of labor, etc. So an aperture array is what, in engineering terms, we'd call a receive-only phased array. And here's an example of one of the early ones. This is the Murchison-Widefield array, which ICRA runs in collaboration with an international support community. You'll see there a large number of pretty small elements. So this is the Murchison-Widefield array MWA dipole. It stands about that tall, and it's about that wide. So it's about just under a meter tall and just over a meter wide. It's essentially two bow tie antennas. It's dual polarized, so you have one in one plane, another in the cross plane, and again, the signal processing is all duplicated, so you have an XY, you have a north-south and an east-west polarization channel and two coaxes coming out of that. This is not RF over fiber, it comes out as RF, The signal comes out as RF, goes into this box over here, which has a hybrid analog or partially analog beamformer, similar to some parts of LOFAR, which was built at around the same time, and actually uses very similar technology. And that is then used to actually steer the beam around the sky. It's important to note the big advantage of an aperture array is there's no moving parts. So the beam steering is done electronically. If you've never tried to maintain something 600 or 700 kilometers away from a major population center and 300 kilometers by dirt road from the closest small town, Geraldton, one doesn't appreciate just how hard it is to maintain a large moving structure. Something like Meerkat, the overall pedestal and dish structure weighs about 44 tons, and the moving antenna alone weighs about 25 tons. So if something goes wrong with that, you need massive infrastructure, cherry pickers, etc., to go and fix that. So this is very attractive. There is one drawback, and that's that you can't scan right down to the horizon. There are projection effects. So the SKA Low's main beam is in a sort of cone from 45 degrees off vertical, or a total cone of about 90 degrees of the sky. So it is not truly an all-sky instrument, but it can see a lot of the sky. And it can see a lot of the sky at the same time. This I'm going to skip, because I think Lewis will be showing this to you, and that's how I don't want to steal his thunder. I want to talk a little bit about the trade-offs. With a dish, there's no such trade-off to make. With an aperture array or an array of any sort, you have to trade off whether you want to work in the dense regime or the sparse regime, and that's determined by whether the spacing between the elements is less than or more than half a wavelength. If it's less than half a wavelength, it's a dense array. You only get one main beam, but you've got a lot of elements, and you've also got strong mutual coupling. If the spacing between the elements is greater than half a wavelength, the array is sparse. Fewer elements, but you get additional main beams called grating lobes. Again, this is basic antenna theory, which most of you will have seen back in courses at university. The mutual coupling is also weaker, but let's say you have this issue with the grating lobes. One way around this is to have a sparse array which you then randomize, which tends on average to wipe out the grating lobes, but I emphasize that's true on average. It's a statistical effect, but you can't always rely on it to do that. There's a bigger problem with SKA low, and that is that SKA manages to combine elements of both these arrays, and that's because it's a very wideband instrument. It's designed from 50 megahertz to 350 megahertz. That's a 7-to-1 band. It starts out as a dense array, and at around 100 to 110 megahertz, it transitions to being a sparse array. So it manages to combine, one would have to say, probably most of the drawbacks of both arrays by this very wide bandwidth. And it's just something you have to deal with as an antenna design. If you want a very wideband array, there's going to be some drawbacks. I want to very briefly touch on mutual coupling. Again, it's a term which is very well known in the antenna community. Essentially, it's normally unwanted interactions between antennas, and it's caused by induced currents on the secondary antenna from the primary antenna. We can model and predict it, that's fine. The problem is that modeling and prediction can become very computationally expensive. Usually mutual coupling is something which antenna engineers do their very best to avoid. There are cases where it's been exploited, and one case, for instance, is to make Vivaldi arrays, especially dense Vivaldi arrays, significantly more compact than would be otherwise. Mutual coupling there is advantageous, but that's a very special case. Usually it's something you try to get away from. And I just mentioned that because we're going to see it coming back to haunt us a bit later. There were a large number of prototypes which were built, and here's some of them. That's the merchant wide field array I've spoken about already. This is one of the very early systems, the AAVS1, Aperture Array Verification System version 0.5. That had only 16 elements. And this was deployed both so we could try out simulation tools and also to see how viable this was in the West Australian desert. This is the second iteration of this, a full 256 array. This now has a ground plane, which this one didn't, and the ground plane is useful to fix the phase reference point. This had 20 kilogram lumps of concrete, bollards, which anchored the antennas down. This turned out to be very problematic, both lugging these things around in the middle of nowhere, and also they were getting broken by 700 kilometers on the back of a truck on very bad roads. Here's another one. We built this ourselves at Cairo at Curtin University. It's the same semi-random configuration, but we used Murchison wide field array, MWA dipoles. And again, Randall, who's in the audience, was very heavily involved with that development. It's called the Engineering Development Array, and it's actually still operational, even though it was built quite a few years back. Here's the one that I've been most closely involved with. This was built in 2019 as a collaboration between Curtin University, or ICRA, and INAF. Here you can see the layout of the antennas. This is a drone shot. These are just bollards which are just popped down randomly. They're not part of the design. The antenna is now clipped onto the ground plane with some clever design which was done in Italy. This is the overall view from the top. Again, you can see it running from approximately 40 meters by 40 meters. Each crossover there is the center point of an antenna. It's not quite to scale. The actual antennas are a little bit bigger than those crosses would indicate, and some of them almost touch each other. So there's quite strong mutual coupling. This is an image of the very last prototype. This was actually built by SKA themselves. This is half constructed. They've got about half, probably about 100 of the 256 antennas have been deployed on the ground plane. And there you can see the older AVS2 in the background. This had a very short lifespan. It ran for about a year or so, and then it was switched off, and a further change was made for the final version, which I'll speak about in a moment. Here I am stealing Lewis's thunder. I'll leave it to him to unpack it in more detail, but this is the first light image, which was obtained just a couple of months back, and I'll leave it to Lewis to explain that to you in more detail, and I'm sure he will. I'm changing gears now and looking at computational techniques. So this field is a well-established field in electromagnetics by this stage. When I was a young graduate student, it was very much a field that was developing very rapidly, but of course, I was a young graduate student many years ago. It's a similar vintage to techniques like computational mechanics, and it shares a number of methods like finite element methods, boundary element methods, which people who work in computational mechanics and computational fluid dynamics will immediately recognize. Whereas techniques like finite element analysis for structural mechanics was very rapidly adopted by industry, indeed by the 1980s, it was a standard design technique. That wasn't the case with computational electromagnetics. And one of the reasons for the slower adoption was the fact that problems were much bigger. With a finite element analysis of a structure, you're only discretizing, turning into a mesh, a relatively small part, which is the structure itself. Whereas with electromagnetics, you've got radiation around it, so if you're using any finite difference or finite element-based technique, you've got to mesh up from free space. And the boundary element techniques are all dense matrices, which result in very high computational cost. By around the mid-1990s, algorithms were developing, and I'll talk a little moment about the algorithm which really made the method of moments or boundary element techniques viable for that. By the mid-1990s, we were starting to see personal computers which had enough power to be able to address those issues. At the same time, commercial companies were springing up, which were actually providing ready-made commercial codes. Back in the 80s, when I started my career, we had a few packages, codes, usually of US Department of Defense origin, like NEC, Numerical Electromagnetics Code, which was a well-known code in the field for many years, and indeed is still used today because it's freely available. But they had very limited, actually they didn't have any interfaces whatsoever. You had to manually describe each point and each node that you wanted to connect up with wires or surfaces. There's a number of commercial solvers now, and it's now, I think, firmly embedded indeed. Whereas 30 years back, someone going out into industry probably wouldn't have had exposure to those. Our students now, if we put them into industry and they don't have access to the code, will promptly say, oh, we can't possibly do this job, even if it's designed a simple dipole. So, over the last 30 years, these techniques have really come out of the research lab and they've become big business in their own right. A lot of this work was originally driven by military applications, and that's why I was working on this years back at CSIR's Defense Research Institute. And that was in particular true in the 1980s when the Americans were developing stealth systems. A number of those were actually verified using computational EM methods. But nowadays, commercial drivers or commercial applications have become the main field of interest. In particular, codes like FECO, which I was closely involved with, were used in, at that time, the rapid emergence of handheld devices. There were concerns about the irradiation of your brain, and we did some work for the South African mobile operators using some of these techniques. And another big application was also in the automobile industry. The German automobile industry were early adopters of very much electronic-driven cars, drive-by-wire, and they had major concerns about radio frequency interference, and they were using simulation tools like this to check out wiring harnesses. Now, it's well embedded. As I say, any RF lab will have some of these codes around. There's a couple of major things you can do with it. Firstly, you can do rapid product development, and also you can do design studies for more exotic applications, in particular military. Problems which, when I was a graduate student, we couldn't even think about doing are now just routinely knocked off. And I actually had a student once port a code onto your phone, and he was actually able to do a finite difference time domain simulation on an iPhone. That was a few years back with much simpler, probably it was about an iPhone 8 or something. So that computation capability lies in everybody's hands nowadays. There have also been very significant algorithmic advances. Some of you will know Zoltan Senders. He was the founding engineer of ANSOFT, which was later on brought up by ANSYS. And he came up, you'll be familiar with Moore's law, processing power doubles every 18 months. It's not actually what he said. He said that packaging density doubles every 18 months. But what Zoltan Senders said is that algorithms are doubling in speed even faster. They're doubling about every 12 months. If you compound that over a decade, you get a speed up of around 100,000. And that's one of the reasons these techniques have become so ubiquitous. We're in the International Union of Radio Science. Everybody's seen Maxwell's equations before. These are the controlling equations. I'm hammering them onto our students right now in the third-year class, which I have to head back to later on this week, although we can't do numerical methods at that stage with them. How have we gone about solving these numerically? We can look at solutions in the time domain, and we can look at solutions in the frequency domain. The frequency domain is mostly the algorithm called the finite difference time domain and the closely related finite integration technique. Finite elements are also very widely used, especially for design of feed structures and elements like mixers and circulators. That's traditionally done in the frequency domain. There are also some time domain ones, and I worked on some of that myself with students a few years ago. But the ones that are most useful in radio astronomy tend to be the boundary element, what we call moment method in electromagnetics. These are based on Green's function propagators, Typically, we use the free space one, but we have other advances like Sommerfeld formulations, which can handle real physical grounds and allow energy to be propagated into the ground. There are also asymptotic methods. These are ray-based, and they typically use things like uniform geometrical theory or uniform theory of diffraction, physical theory of diffraction. These are all essentially ray-based techniques, and I'll touch briefly on those for dishes where they can be very powerful. At very high level and very superficially, if you're not familiar with the methods, if you want to look at scattering from a sphere with a method of moments surface solver, you mesh up the surface. With a finite difference mesh, you'd mesh up the volume with cuboidal elements, and with a finite element, you'd mesh it up with tetrahedral elements. That's a really crude description. Nowadays, many of these techniques have been hybridized with each other. In particular, finite element and moment method were hybridized many years back very successfully. But at heart, those are the techniques that are around. The method of moments, which is the one I'll be talking about in a little bit more detail for radio astronomy, is essentially based on this either thin wire or a surface formulation. And what you do is to have some known field, which you can derive from electromagnetic considerations, solve for the unknown current by numerically approximating it as a large number of segments or triangles if you're working on surfaces. That uses RWG elements, which again date back to the 1980s. And the result that comes out is a surface current from which you can compute the parameters you're looking for. You do get a computationally expensive method. With n segments, you have n squared memory usage, and more importantly, n cubed computational cost asymptotically. That was a major issue, and in the late 1980s, a fantastic method came around, the fast multipole method, the MLFMM. This is its multi-level variant. It was derived by and first published for electromagnetics by Griegard and Rauquelin, and it's viewed, I think, as one of the top algorithms of the 20th century by some of the maths journals. The essential idea is to reduce n squared dense interactions to asymptotically n log n interactions using a process of aggregation and disaggregation based on expansion of the fundamental electromagnetic propagators, the Green's functions. That's, again, a really superficial view of the method, which has absorbed people for many, many years to study, understand, and implement efficiently, but without that, we'd be unable to do the very big problems we're doing in electromagnetics. Here are some of the leading companies in the field. HFSS, the high-frequency structure simulator, is now owned by ANSYS. It was set up by ANSOFT. The FDTD, perhaps the best-known one, is Microwave Studio. For many years, CST developed that. It was recently bought out by Dassault Systems, a massive French multinational. FECO, one that I was very closely involved with, has a really interesting history of corporate takeovers. It was developed by a small South African startup company, EM Software and Systems, in collaboration with the University of Stuttgart. That was bought out about 12 years ago by Altair, which was a large American multinational, and a few months back, a really large German multinational, Siemens, bought out Altair. So it's now part of the Siemens simulation packages. There are also, a lot of these codes now are hybrid codes. FECO, for instance, has method of moments. It has finite elements. It has hybrid method of moments and finite elements. It's got some asymptotic methods built into it. And I would just highlight one code which I haven't spoken about, which is GRASP, which is developed by TICRA. This is an interesting company because it's actually owned by the employees, and it's a company that apparently they're not allowed to sell. So it's one which is not going the route of all these other companies, which have become part of larger and larger multinational multiphysics programs. That's got some really nice implementations of asymptotic methods and method of moments, and people like Dirk de Villiers have used those very extensively for dish analysis. I want to talk quickly about simulating radiation patterns with computational electromagnetics. Those of you who attended the Young Scientist program yesterday, I just assumed we knew what the antenna patterns looked like, and I didn't talk about that at all. Now we need to talk about how we get that. Here's a really long list of references, which I'm not going to be able to go through in detail, but I want to give you a flavor of the development of this work. This has been recorded as far as I know, Peter. So you can take a look through these references a little bit later. Something which I think you will notice is the first references I have there are from around 2008. And the one that's in black, Jacob Barr's paraboloidal reflector antenna, is a classic, but it doesn't actually use full wave methods. It's using asymptotic techniques, ray optical techniques, and diffraction methods. So all the other ones essentially look at using full wave techniques, and they started out looking at feed structures similar to the ASCAP structure. In that case, it was for an array called Upper-Teef, which Astron built. You'll see some papers by, the fourth paper there is by Dirk de Villiers. That's one of the first ones, I think, which was applying a full wave technique to dishes. And then there's a variety of work from colleagues at Stellenbosch, at Astron, and Chalmers, running right down to recent work we've done with INAF, that's the work with Pietro Bolli, and also work with Carl Warnick in the United States. So I won't unpack those in detail, just to mention that there's been a significant amount of work, but it's all relatively recent, and that's because we really only had these techniques available in the last couple of years. They've also been used to design feed structures, and these feed structures could be, for instance, variations on horn structures, and the last two papers there by Robert Lemzik and Dirk address actually variations on horn design. And the very last paper there is from the Chalmers group in Sweden, where they're looking at quadruple ridge flared horns. There are also papers there, Stuart Hay et al.'s paper, that connected patch array analysis is the 192 element feed which ASCAP uses, and the very first references there, the first two essentially deal with the Upper-Teef focal plane array, so it's another type of array which goes in the focal plane of the systems. Here's some very early work, which this was 2015, this was done about 10 years ago, and you'll see one of my former postdocs there, and interactions with Stefan Van Holtz and other teams from, the others were at Astron and Chalmers at the time. And we were looking at ways to try to study what the low band array looked like. The low band array is the one on this side, and I think it runs from just under 100 megahertz down to around 10 or 20 megahertz. These are the element beams for each little element. And if you look closely at them, so these are simulated by terminating all the other elements and just having one switched on. And then you repeat this for all the elements. And you'll see that some of these beams actually squint significantly towards each other. They're not supposed to do that. It's the interaction or effective mutual coupling which is causing that. Some of the very early work on looking at this continued. My colleague Adrian Sotinjo, I'm not sure if he's here, you heard he had an injury just before this conference. He looked at methods to handle the 16-element log periodic array, and a lot of the techniques he developed, we've actually continued developing for SKA. A couple of years later, Martin Sokolowski and others at Cairo developed methods to produce full embedded element patterns for the Murchison-Whitefield array. So we drew on quite a lot of existing work when we were confronted with a 256-element array of these very complex Scala 4 antennas. When I first saw these, I thought this is not going to be possible to simulate, but it turned out we were able to do it just. There's a lot of stuff that you want to do with this. If you want to simulate that full station, you've got to simulate 256 times 2, because you've got two polarizations, and you need the pattern from each individual antenna. That sounds like way over the top, but I'll show you in a moment why we need that. We use the method of moments. We use it with MLFM acceleration, and there's a reference there where we describe in detail how we did this. I'm just going to skip over embedded element patterns, just to mention briefly the idea there. It's an active array pattern, so you terminate all the other elements, you have one element switched on. There's a couple of ways you can do that. But because you have to repeat it for each element, it's quite computationally expensive. This is the FECO model that we used, and it was developed by one of Randall's interns back in about 2019, and we were able to take a model which exported it with about 30,000 degrees of freedom from the mechanical CAD model. We were able to reduce it to around 12,000 models. And of course, it was verified in an anechoic chamber. Put all this together, and you're dealing with a problem with around 2 to 3 million degrees of freedom. Now, for a method of moments problem, even with the MLFMM, that's a big problem. The MLFMM has another issue too, because it's an iterative method with an unknown rate of convergence. Sometimes it converges rapidly, other times it can converge quite slowly. We've expended many hours, I think thousands of CPU hours, and we've got this ported onto supercomputer systems, both POSI and also commercial systems. This is not a rapid thing. It takes us about as long to simulate this as it takes to build an array, but we have got faster at simulating it. I mentioned, why are we doing this? I mean, can't you just say these antennas are more or less the same? We'd love to do that. This is an isolated element pattern. That's one Scala 4 antenna on a ground plane. There's its pattern. Add all 256 of them together with appropriate phase steering. In this case, there's no phase steering at all, so the main station beam points vertically upwards. with the side lobes. That's great. Why don't we just do that? The problem is, unfortunately, the patterns don't look like that at all. Now, I'm showing you a pathological example. This is one of the worst frequencies. It's not always as bad as this. But at 70 megahertz, this is what the patterns actually look like for individual antennas. So they're supposed to look like this. They actually look like these really weird sort of tulip shapes. Now, I'm sure a graphic artist or someone from fashion design would find this great. For an antenna engineer, perhaps not so appealing. So this is why we have to do this. Very often you can go and average things out, but it's not entirely true for these patterns. And unfortunately, when you average these out at some frequencies, the results are not correct. You might also ask, we're scaring people with these terrible patterns. Are they actually correct? Because they look so wrong. I think we had quite a few people saying, not sure we believe that. So fortunately, our colleagues at INAF had developed a drone. They were able to make measurements. This is a cross-section of some of the drone pattern measurements that they made. This was back in 2019, just before COVID broke out. And the line with the squiggles, this is both a decibel plot in different pattern cuts for two different antennas. The agreement is actually very good. The reason for the squiggles is there's difficulty with the height keeping with the drone, and more importantly, the wind was, of course, starting to blow. So they were having atmospheric condition problems. Nothing surprising when anybody who's ever tried to make an outdoor antenna measurement. Now, this is a picture of why these issues evolve. So here's one of my colleagues. She was at SKO at that time, Maria Grazia-Labate. She is making some final adjustments to an antenna. But you'll appreciate this is almost a sea of antennas. These are really close together, especially the lower frequency bottom eggs. This was exacerbated by going from a 5-to-1 bandwidth with a lower frequency of 70 megahertz to a 50 megahertz lower bandwidth, which made the bottom beam significantly larger. And that's where this very strong mutual coupling came from. A variety of techniques were looked at to try to ameliorate this. This was the design that we spent a lot of time simulating. Let's say the AVS2 prototype ran for about 4 years. Shortly after COVID, there was a suggestion that we should look at this thing called a Vogel or sunflower pattern. It's been used for dishes, which have very little mutual coupling because they're far apart in terms of wavelengths, and the beams are very largely very directional. The first time we saw this, we said, we think that you're going to have problems because there'll be strong mutual coupling at some frequencies, and indeed that was the case. And the final pattern that's been selected is one given over there. It is a variation of this sunflower pattern with some randomization, and it actually, at the end of the day, is actually very similar to the second prototype that we built. This layout over here with some rotations, which Lewis may or may not describe later, and I can talk about after the talk, this is the pattern that's actually been used for all the SK low stations. This is what a station beam looks like. This is an orthographic view, so if you're not familiar with this, what we have got is it's against direction cosines, effectively. The vertical, so straight up, is in the center of the plot. The horizon is over there. It's only a hemisphere because with anything that's Earth-based, you can only see half the sky. And the blue over there shows these pretty random side lobes, which the AVS2 quasi-random layout is supposed to have caused. These eventually get multiplied out in the whole interferometric array, so the idea is that they will eventually tend down to give a very low level of pattern, except for the main beam. The AVS3 had what looked like a nice pattern. In a smaller talk tomorrow in Commission J, I'm actually digging a bit more deeply into some of these designs. But I will mention that one specific frequency at around 125 megahertz, this regularity caused a serious issue, and the zenith gain dropped by about 50%. So I'm not showing it here. I'll talk about it in more detail tomorrow. It's a specific design issue, but the regularity did cause issues. Even though this looks good at a particular frequency or band of frequencies, it wasn't so good. The final design, the station configuration as used, is this one over here, and it's actually very similar to the second prototype, which was extensively tested. I also want to mention very briefly some other applications. Dish work. For many, many years, all dish design work was done using essentially optical techniques. Some subtle second-order effects started evolving, and here I particularly fished out some work by Dirk, who's sitting right at the back there, Dirk de Villiers. This was an analysis of the offset Gregorian meerkat configuration. There's a very subtle ripple in the aperture efficiency, and Dirk was able, using full-wave simulation methods using MLFMM, to actually predict this and then develop a simpler model for this, and which is a really nice thing to do because then you can design around it. Now, this is Dirk's work, as he is here, and I'm not going to discuss it in more detail in case I explain it incorrectly. So if you want to ask him, he's sitting at the back smiling. This was really nice to see. I think it's the first full-wave analysis of a dish for radio telescopes. Some other work was also on the go in South Africa. This is the precursor to Meerkat. It's the Karoo telescope. This was a traditional centre-fan paraboloid 12-metre dish. This is actually not a radiation analysis. This is a lightning strike vulnerability or EMI type analysis. The mesh is significantly coarser because the frequency content of a lightning bolt is significantly lower than the operating frequency of the dish. And this work was done by my colleague Howard Reeder, who many of you will know from URSI, and Gideon Veet, who's also quite well known in the field. And that result was then used to allow them to optimize some of the shielding. Another SKA prototype was the mid-frequency aperture array. This was supposed to fill the gap between SKA low and SKA mid. It was designed out of the project due to budgetary constraints back in about 2014, 2015. But it was a very interesting system. This is a prototype which Astron built. This is the Embrace 20,000 element prototype, which was built, I think, in around early 2010, Stefan? And it ran for several years and produced some interesting data. These are very densely, closely packed, dual polarized Vivaldis. It actually only had the electronics for one polarization, but it was just because of lack of budget. It had both polarizations designed in. How do you analyze something like this? And one method, this was derived originally by Rob Marskant and Raj Mitra, is to use techniques which essentially develop macro basis functions. This is a characteristic basis function method, which a lot of these techniques are variations of. And instead of having these very small triangular patches, you still have them, but you build up a bigger, often geometry-based macro basis function, which might, for instance, span a whole array. It's more difficult to see how to do it when you've got these connected arrays, but it can be done, and it gave efficient results. I'm not going to unpack this in detail. These particular results were done by Dani Ludik, one of my former PhD students, who now is I think, the Chief Executive Officer of Ixis, the company, and he'll be here tomorrow if people want to ask him more about it. So I think my time is about up, so I'll wrap up. There's little question that in the last 10 to 15 years, our ability to use computational methods for both dishes and aperture arrays has revolutionized our understanding of what's going on with these systems. We're particularly proud of the fact that with the AVS3 prototype, we were able to predict a problem before it was actually observed. And I remember being very excited when my colleagues from SKA told me, yeah, we've seen exactly the same effect that you guys were predicting. This is important. SKA low, if someone had said, let's rather put 500 of those antennas in, we would not have been able to simulate it. So it was rather fortunate. It actually just happened to be about as big as we could realistically simulate at the time. And I mentioned that it's actually impacted on both the calibration and commissioning. I didn't talk much about the calibration, but these patterns are also extensively used, sometimes in average form, sometimes individual patterns, by the team that is doing the SKA low calibration. And there are people here, Randall and his colleagues, who are working on that. Looking ahead for next builds, or for instance, upgrades of these systems, it would be really neat if we could incorporate these types of things earlier in the design cycle. The issue at the moment is the analysis time is simply too long. We're talking of months of analysis time to generate all the frequency data we need for something as big and complex as the SKA low. Now, from an antenna engineering perspective, it's partly our fault. The Scala 4 is a complex antenna, and if it was a simpler antenna like the MWA, we'd have been probably able to optimize more than we were able to optimize with the SKA low. I'll wrap up and once again acknowledge the very large number of engineers from around the world that I've interacted with in this project, and also commissioning scientists and scientists. It's been a really rewarding period. I have an acknowledgement of the observatory. I would like to acknowledge the Wajari Yamati people. They're not just the traditional owners, as is normally the case in Australia, they're actually the native title holders of the observatory site, and that's a significant difference. The picture credits here are from a variety of sources. I've mentioned them over there, and a number of them I've taken myself as I've had the opportunity to visit a number of the sites. Thank you very much for your attention.
Thank you, David. That was a very interesting overview of developments and where we are in the building of these structures. I'd like to ask for questions from the audience. George, there should be a roving microphone.
That's okay, I can speak loudly.
Okay, thank you.
So you mentioned your talk was geared to the design of their base. Could you make
Not
some
loud
comments?
enough, get a microphone.
Ron's taking you on there, George.
Could you make some comments
I'll repeat the question, Ron.
could you make some comments on the noise in the measurements?
Good. So the question that George asked was, for that, I think the measured result that I showed with the drone, what sort of analysis of the error, what measurement error did we have there? I have to say there, we kind of have to do it backwards. We kind of use the computational methods to evaluate the noise, even though we're supposed to be verifying the computational methods with the measurements. That very rapid ripple that we were looking at has a magnitude of around 1 or 2 dB, and that is easily caused by minor variations in the height of the drone, in particular in the presence of strong winds, which was the case when those measurements were made. That was about as good station keeping as was possible. There are some more sophisticated techniques using lasers to track very carefully where the drone is. One issue you have in Australia is there's very strict drone legislation, so it's very difficult to get permission to operate at the sort of altitudes you need to operate with these systems. Other countries are more relaxed about it. But sorry, that was not a... So that measurement was out in the open in bad conditions, and conditions which were getting worse with a rainstorm approaching.
Other questions? One over here.
Yes. I'll repeat the question for the audience. All right. So the question was about how we did the analysis. So the analysis is done in particular using FECO with the MLFM deployed on parallel, initially with a workstation which had about 50 threads, 26 cores if I remember correctly, and more recently it's been ported onto a system which is run by actually a group of geologists. It's called DUG, from Down Under Geophysics, a lovely pun, because that's what they do, they dig in the soil. And these guys run one of the more powerful, perhaps the most powerful commercial supercomputer in Australia. And they've got a variety of different systems running a variety of different Xeon-based and also GPU-based systems. So we have FECO running on that system, and we're able to do the analysis with that. But as I say, one of the issues is because the antenna is a complex antenna, we need somewhere in the order of 12,000 degrees of freedom. If you're familiar with FECO, it's segments and triangles that we're doing. And unless you have a simpler antenna, or you have fewer antennas, you're going to be sitting with complexity. Even there, we've simplified the model. For instance, our ground plane, which is in reality a finite ground plane with real Earth beyond it, that's not what we're modeling. The MWA models, we actually include the finite ground plane and the effective real Earth with whatever the values of conductivity and dielectric constant are, and they vary depending on the soil conditions. So it's difficult to give really accurate results because sometimes nature changes stuff on you.
Thank you. Another question? Yes, over here.
No. So essentially, remember the highest frequency there is 350 megahertz, so the wavelength's about 1 meter. The soil is actually, sorry, let me just repeat the question. The question was, are we incorporating the effects of ground roughness in the simulation? The answer is no, for 2 reasons. The first reason is the ground has actually been prepared before we put the ground plane down. So you're not just throwing, for instance, if you take a look at that picture, I'm actually going to jump back to one of the earlier pictures. The system's not paging back as rapidly as I'm trying to make it do. Yeah, that's what I wanted to show. So this over here is essentially prepared ground on which the ground mesh is put. And the preparation is probably accurate to within centimetres. Someone from SKA might care to comment on this a little bit later. I don't know exactly what the specification is. The area is incredibly flat. I took a number of the station elevation heights, and over a distance of kilometres, the difference in elevation height is of the order of a few metres. So it's essentially at the same level. But as I say, with the shortest wavelength of a metre, we really don't need to concern ourselves with very minor variations in the soil. So the soil quantities, for the SK simulations, we've just assumed a perfectly electric conducting half space. We have more accurate simulations, the MWA, and it actually has a smaller ground plane, so it's more important there. But even there, say you have unknown quantities in terms of what are the specific climatic conditions you're dealing with at any given moment. Because when the soil gets wet, it gets waterlogged and stays that way for weeks. In the middle of summer, it's baked sand. Good. So the next question was, do we compensate for the edge effect of the finite ground plane? Again, with the MWA, yes, we do. With the SKA, no, we don't. There have been a couple of simulations done, and we're looking at that again at the moment. There was a theoretical publication around that using some formulations a little while back, but that's a long way from being incorporated into commercial code. The issue with this is there's some really neat ideas around that would make it much faster, but the antenna is so complex, you can really only do it with a commercial code like Pico.
Okay. Are there any more questions? Oh, one more.
I've actually got two questions.
Well, Scott, let's make it one. I'll do the other one over tea.
All right, excellent. Okay, we'll do the first question. It's actually Commission E related, relative to electromagnetic compatibility and radio frequency interference. I want to know what measures are in place with the Murchison Wide Field Array outside of being fairly remote to deal with external interference with the radio telescope.
All right, so I'll repeat the question, and I say this is one of my colleagues from Cairo, which is why I told him I'll take the second question over coffee. So the question was, what measures are we taking to protect systems such as the MWA and also ASCAP, which is operating at the same time, in particular from construction activities? Well, this is a problem on the South African side as well. It's probably better to have someone from SKA comment in detail on this. But essentially what you have to do is, during the day, you're doing construction activities, and if you're able to make measurements, fine, you can. If not, you have to wait till nighttime. The viewing conditions in any case are better at night, and construction is normally not done at night. So that's essentially an answer to that. The biggest single source of noise at the moment is construction activities. There are other things you have to concern yourselves about as well, and colleagues in South Africa looked at some other things like electric fences, which are used for controlling jackals. That's not a problem on the MWA site, or at least on the Murchison, because there's no farming activities there anymore. Right.
Okay, well, let's wrap it up. Let me thank Professor Davidson for a really interesting talk on the present state of computational electromagnetics and the design of the SKA low and related structures. So, thank you, David.
Thank you.